All right, real quick. Those of you who are handing in the quiz physically, you can do so in this pile up here. Just make sure you do it before we all get out of here. Then I'll try to get those graded and get your feedback sometime today. All right, so any questions before we, there it is. Any questions before we get going? All right, just a reminder, it's a little bit. I think it's 2 weeks from Wednesday. Or is it? Yeah, 2 weeks from Wednesday. All right, so we're starting section 6 is our last section from chapter 1. Before we get into actually doing derivatives. Here we go. So I think we have looked at this before. This limit here. But let's just remind ourselves what happens as x gets closer and closer to 0 here. What is it? Closer and closer to infinity, which is, I'll go ahead and word it as it gets larger and larger, right? So maybe a graph is helpful here. So yeah, as I get closer and closer to x equals 0, then 1 over x squared gets closer and closer to, or it gets larger and larger. I can make the value of this function as large as I want. So I think we've seen this, understand how that works. What's this limit equal to? Infinity, right? Because it does not matter what happens. So if I approach from either side, it just stays positive, gets as large, just arbitrarily large. So when I say this limit equals infinity, am I saying that limit exists? No. I'll just make a note here. The limit does not exist, but I am just being specific about how it fails to exist. So any questions on this first example here? So these are really limits we haven't spent a ton of time on in the last few lessons, talking about these limits that do either increase or decrease without bound. So that's what we're going to get into today. So let's find these 3 limits here. For the first one, limit of as x approaches 3 from the right of 2x over x minus 3. How can we go about this? If we're tying it back into what we did last time, is this continuous? And x equals 3. No. And really, what kind of continuity am I looking at here with that limit? Not necessarily. There's one specific, or a couple of different specifics when we talked about community on Friday, or continuity. This is right continuity. So we can talk about continuity in general, or we can talk about continuity from the right, continuity from the left. In this case, this is continuity from the right. So what happens as x gets really, really close to 3 from above? Value is greater than 3. Okay, I got 1 vote for approaches infinity. And I think probably the easiest way to look at that is to graph it or plug in some values, 3.1, 3.01, so on, but you'll see this behavior here. In fact, let's just look at, f of 3.01, you're going to get 6.02 divided by 0.02, which is going to be, it's going to be positive, and I can make it as large as I want by getting closer and closer to 3. How about from the other side? It's a good test value for me to not, I mean, not that 1 point can really tell us anything, but yep. So anything, yeah, anything near near x equals 3 from the left-hand side, that comes out to be what, 5.98 divided by negative 0.01. That's clearly going to be negative. Can I make that? Can I make those negative numbers, you know, as small as I want to? I can, yeah. So again, from the left, I can get as close as I want to x equals 3. And I can get this limit, which I don't know if we've looked at one that behaves that way yet, but typically when you write infinity, you're really saying, really what we're saying is this, even though it's implied. You can have both of those ideas, positive infinity or negative infinity. Then what does this mean about this bottom limit here? I can't tell you anything about it. So the left hand, no, sorry, the one side of limits don't agree. The limit doesn't exist. Try that n again. But absolutely, yeah. So yeah, the top two. So none of these three exist, right? None of these three limits. But I am just giving you more detail. For the bottom one, I can't really. There's no consistency from the left hand to the right hand. All right. So let's talk about asymptotes. So you've probably, no, I'll say you've almost certainly seen these before. But an asymptote is a line that a graph approaches but never reaches. I'm guessing you've dealt with these quite a bit, but not in the context of limits. Go ahead. This is 1/6.
1/6.
Yeah. So another way to think about this is the distance between the line and the graph is always positive, but I can make it as small as I want to. So let's look at just in the margin here, f of x equals 1 over, I'll do 1 over x this time. So two different asymptotes here. I can get it as close to the y-axis as I want with that graph. I can never reach it, but I can get as close as I want to it. Same with the x-axis. If I make my x values very, very small or very, very large, I can get as close as I want to the x-axis, but I can never reach that one. So vertical asymptote. Graph approaches a certain value of what? So if I have an asymptote that's vertical, which in this case, this is a vertical asymptote. Am I getting am I really getting really close to an x value or a y value? Getting close to a certain x value as the y values get arbitrarily large. And I really should put this here, arbitrarily large or small. The y-axis from. And a horizontal asymptote, kind of the opposite relationship here. I get a graph that approaches a certain y value as the x values get arbitrarily large or small. These definitions y'all have seen before. Totally mysterious. They're not. All right. So let's look at some infinite limits here. So this function here, f of x equals the tangent of x. Where are the vertical asymptotes? There's something we remember, something we need to draw a graph to help us figure out. Yeah, right. Yeah, that's what I prefer. Okay, so I got some votes for x equals 0, x equals pi. Are there others? How many are there? Infinitely many, right? They show up regularly. So, and just to kind of talk about how we know that, tangent is one of those, and we understand tangent, we probably understand other functions that that kind of give you tangent in a more straightforward way. Is there another way I can represent tangent? What was that? Oh, 1 over cotangent. Yeah, that's true. That's not what I was going for, but thank you. It's actually sine over cosine. So if I have sine over cosine, when is cosine of x equal to 0? Yeah. No, it's fine. I would bet money that you weren't alone on that one. So x equals pi over 2, 3 pi over 2, and so on and so forth. But bottom line, how far apart are these asymptotes that show up infinitely often? Yeah, they're pi apart, right? So not 0 and pi, but I can list them out like this: pi over 2, 3 pi over 2, 5 pi over 2, and so on. Or if you prefer, pi over 2 plus k pi. K is an integer. Did you get arbitrarily high or low, depending on where you are? Yeah, this trig function has an infinite number of vertical asymptotes. How about this one here? So I got a couple different questions here. What happens to f of x as, the way I worded this was the absolute value of x is very big. So as I have very large positive numbers and very small negative numbers. So let's answer that kind of one piece at a time here. But here's an idea that I know we haven't looked at yet, is now I'm asking, if I want to know what happens as x is getting very, very large, what am I letting x approach? This time I'm letting the base, or kind of my input variable, my independent variable, go towards infinity. So what is the limit as x goes towards infinity of x squared minus 1 over x squared plus 1? Where is this function continuous? You got a lot of votes for everywhere, right? I cannot make that denominator 0, so it's going to be defined everywhere. So it's continuous everywhere, which means you can't plug in infinity, obviously, it's not a number, but you can plug in some values and you get kind of an idea as to what happens here. So what happens if I plug in a bunch of really large numbers? What is this thing starting to trend toward? Let's look at f of 100 and f of 1,000. Should be 0. So f of 100 is going to be 10,000 minus 1, so 9,999 over. So that is incredibly close to 1. This one's going to be even. That's going to be 999,999 over 1,000,001. So a couple of different ways we're looking at this, and we'll, just like everything else we've done, I'll give you more sophisticated methods later, but the limit as x goes to infinity for this function is 1. Another way that I like to think about these is this. Look at the numerator let's just look at the numerator first. As x gets really, really big, what effect is that -1 going to have on the rest of the numerator? Yeah, it's going to be getting more and more negligible as x gets bigger, right? Same with the denominator. So basically, you have a function that as x gets bigger and bigger, the -1 and the +1 are going to get overwhelmed. So you're just trending towards x squared over x squared. Do we need to look at what happens when x gets really, really small? Why not? Right. So yeah, we basically looked at that already. If we're going to square a bunch of large or a bunch of very small negative numbers, we're going to get positive values in the end. So I have limits. Basically, this limit's equal to 1. So maybe I don't know what this graph looks like. Like, I don't really know what's going on in the middle of this graph, but I know that as I go, very far left, I have something like this. And as I go very far right, I have, something like this. So what can I say about the asymptotes for this function here? So I got a horizontal asymptote. And I heard someone say horizontal asymptote at 1. But I want to be a little more specific than that. Yeah, y equals 1. Even though you said horizontal, I mean, you can, I'm sure you thought it even if you didn't say it, but I have a horizontal asymptote, y equals 1. Do I have any other horizontal asymptotes? Nope. And I just looked at the limit. I just looked at what happens when x gets very, very far away from 0. And I only found, how many limits are you going to find? So yeah, when you look for a limit, you're going to find one limit, or you're going to find what? Or that it doesn't exist, right? So yeah, there's no way for that. There's no way for me to have many horizontal asymptotes. Do I have any vertical asymptotes to think about? Nope. And that's kind of what we, when we mentioned that this is impossible. We're implying. Like what?
I've seen a couple of graphs where there's the horizontal asymptote one that's around the horizontal asymptote.
Is this kind of what you're describing?
Yeah. And then it repeats itself over.
Okay, so I said a function can only have one horizontal asymptote. Does this make that incorrect? Why am I still okay to say that? This is not a function. So you're absolutely right that there are curves that look like this. And if you, I don't really even know if you can talk about asymptotes in that context, but there are certainly, kind of an upper bound and a lower bound. But when you're talking about functions like that, they don't really have. They're not functions. There's some other kind of relationship, but they're not functions. Yeah. Usually a logistic graph, I'll have to think about that. That's an interesting idea. But usually when I think of logistic graphs, we don't think about what happens for very small x values.
Okay. So it's not necessarily like a limit in that.
Right.
Okay.
But I'll have to think about that because I haven't thought about that. Did you have a question? Oh, okay. All right, and I'll just make a note here since I drew it. Not a function. You have a question?
Not gonna decide because x0 is negative.
Yep, that's a good call. Okay, good. Doesn't this graph kind of look like this? Crosses the origin and meets back up? Yeah. All right, thank you for that. All right, any other questions about this thing? So, and just a few graphs here for all of these, the limit as x approaches infinity of f of x is equal to L. And one thing I want to be cautious of, you know, the way that asymptotes are usually phrased or usually defined, including the way I just defined it, was that you never reach that value. And really the bottom line is you want to have a value that you approach as x gets really, really big, but never reach. So in the second graph here, that kind of goes along with the way that I stated it. On the first and third graph here, I am looking at what happens as x gets very, very big. So even though I have these values here, and those of you guys who are your engineering majors, you're going to see these damped functions a lot. But even though I have all these, like an infinite number of crossing points at that limit, you can still see that as an asymptotic relationship. You can make that get arbitrarily close to that level. And the reason I bring this up, I feel like we think that since they're asymptotes, we can't ever reach those y values, but it really is all about this idea here. What happens when x gets very, very, very big? We okay with that? All right, more limits in infinity. So, now I'm now realizing I need to revise something that I said to you. So here I have this. The limit as x approaches negative infinity. Let's just get these two ideas, these two limits. What is the limit as x approaches negative infinity of f of x and positive infinity of f of x? How about when x gets really, really, really small? If I let x get as negative as I want, just going to approach 2, right? How about when x gets very, very large? -1. So I'm going to revise what I said. I think what I said was, correct me if I'm wrong, it's on videotape now, but I think what I said was you can only have one horizontal asymptote. And really, I need to revise that by saying this. You can have this situation, the limit as x approaches negative infinity of f of x might not be equal to the limit as x approaches infinity of f of x. And one example that was brought up was those logistic functions, which very much behave like this. I'll just kind of sketch a quick example of them. But usually what a logistic function looks like is you have some capacity above, some capacity below, which is usually 0. I'll just make it 0. But you have a curve that looks like this. That was my mistake. You absolutely can't have 2 horizontal asymptotes, but as you'll see, The difference is what is x approaching? What am I doing with my independent variable? Is that better? Sorry for lying to you. Any more questions on that one? All right. So let's find all the limits involving infinity on this graph of this strange looking function. When you got one, just go ahead and blurt it out. Let's do limits first before we handle the asymptotes. I mean, they're going to go hand in hand. So, let's go with that. You said x equals -1. Let's rephrase that as a limit of some kind. Limit as x approaches -1 of f of x is infinity. We agree with that? Cool. All right. I think there's at least one more. Do you have your hand up in the back? Yeah. Oh, sorry. Negative infinity, +2. I see at least two more. The limit as x approaches 2 of f of x is equal to infinity. No, yeah, so it cannot be more than one thing. This one just fails to exist. I mean, it's worth talking about because there's a discontinuity there, but that limit fails to exist. Because, yeah, absolutely, you're right that the one-sided limits, I could definitely express them totally different. And one more. Go ahead.
I think it's -1 equals infinity. I just can't really see the graph.
Oh, you know what? I think that one's been handled.
Oh, has it?
Yeah, that one's been given. The limit as x approaches infinity of f of x is 4. Yes, that's 4. Okay. I believe that's all of them. Do you agree? Oh, go ahead. Yeah, so let's unpack this one a little further. The limit as x approaches 2 from the left of f of x is what? And then the other one from the other side. Yeah. So if I want to break it down into left and right hand limits, I can give some specifics. But then when I try to express the two-sided limit, that lack of consistency means it just doesn't exist. All right. So for every one of these limits involving infinity, I can now, these kind of go hand in hand with an asymptote. So this first one, as x approaches -1, the limit's infinity. Go ahead. Yes, those are, if I say the limit is infinity, that still means it doesn't exist. So, and let me say it the more positive way. I can talk about how it fails to exist, but when I say a limit exists, what does the limit have to look like for it to actually exist? Yeah, it just has to be a number, right? It has to be a real number. So, for example, the second and the fourth one down, those limits exist. As x goes towards negative infinity, the limit is 2. As x goes towards positive infinity, the limit's 4. Those limits exist. All right. Oh, asymptotes. So how can this first one here, what asymptote is that limit suggesting the existence of? I got y equals -1. Really should be x equals -1, right? So what kind of asymptote? So basically we have x going towards a number. The limit is infinite. What kind of asymptote are we looking at there? Vertical or horizontal? It's actually vertical. I know, so I totally get it. We think x is a horizontal thing, right? But if you give me a single x value and graph it out, x equals -1 looks like this, right? That's a vertical line. How about the next one down? Limit as x approaches -infinity of f of x is 2. That's y equals 2. So in this case, I'm letting x vary to the left as much as I want, right? And I'm approaching a single fixed y value. So that is this line here. Y equals 2. So this is x, that was x equals -1 vertical. This is y equals 2 horizontal. How about this third one here? X is equal to 2, vertical or horizontal? And finally, right. And just a little reminder to be careful with the horizontal and vertical. There's nothing saying you can't graph these out to kind of help you. But it all comes down to, which one of my variables is going towards infinity? Is it x or y? That's going to govern what kind of asymptote you're going to be looking at. Yeah. So, well, let's break it down. These top two are different in that regard. Yeah, I'm always looking at what is x going toward, because when we look at functions, that's just typically what we do. What is the independent variable doing? But in the first case, x is going towards a number, and y is not limited. And the second one down, x is not limited, and y approaches the limit. All right. Anything else? I think I accidentally did this a minute ago. So the function 1 over x, what happens is x gets really, really big. Right. No, this is not what I did. This just looks pretty similar. So this limit is equal to 0, right? If I'm dividing constant 1 by bigger and bigger numbers, bigger and bigger positive numbers, I get very, very small. How about from the other direction? Or if I let x get really, really, really small, what's that limit going to be? Also 0. So are you ever going to reach 0? Is this an equation that has a solution? And for the 15th time, just reminding you that just because a limit exists doesn't mean your function ever gets there. Another one of those cases, now with infinite limits. Any questions here? Okay. All right, this weird thing. I want to know what happens as x gets Any ideas how we can go after that? Go ahead.
Looking at like the front of each of the numerator and the denominator, x is to the same order, so we can just basically divide it, and since it's 3x squared over 5x squared, it would be 3.
How do you feel about that? I got a thumbs up. I heard someone say no. Go ahead. Right. Right. And a while ago, I showed you a much simpler looking version of this, but the idea is still there that, and I'm going to write a term here that is probably somewhere in your memories. I'll just call it the leading term. Do you remember what that means? The leading term of the leading term of a polynomial? It might not be the first one.
It's always the one to the highest one.
Yeah, it's the one with the highest power of the variable I. So in that case, basically what I'm saying is this: the limit as x approaches infinity of this thing here is equal to the limit of this. Are we okay with me saying that? Right. And so that's something I can guarantee because I understand how polynomials and rational functions behave. One disclaimer I will give is that I am by no means saying this. So their limits are equal, and I know this is are we okay with that rationale? Or we would say that basically as x gets big, as x gets very large, then those other terms that are to lesser powers, or especially the ones that are constant, they're going to get overwhelmed. So this is going to, as x gets very, very large, it's going to approximate the rational function that only contains the leading terms. Go ahead.
Yeah, so I'm saying these limits are equal, right? My function is 9. If I'm making the limits
Tend towards the same number. Good question, though. Any questions before I go on? All right, this thing here. It looks like it should be easy, but it's just not. Any ideas on how to think about this or how to deal with it? Go ahead. I don't think you can do that. Here's what I think just got suggested. Maybe if I'm wrong, correct me. If I completely misunderstood you, I'm sorry. But this right here cannot be done. I'll say this though. This can be done. This the limit as x approaches infinity of this square root the square root of x squared and the square root of 1. well, I can do this. I can just do this and then take the square root of that entire limit. That's fine. Well, it would be fine if what was true? What is the limit as x approaches infinity of x squared plus 1? Positive what? But for you to tell me the limit exists, it has to be, you have to give me a number, right? In that case, the limit doesn't exist, so I actually can't go after it with that either. An idea?
P squared, just taking. Just say that like infinity squared is going to be the square is going to be a number plus one.
Right.
Just get rid of the one and then to square root of that big number. You eventually come back to getting close to like the original number, and then that one is the original number.
So basically what he's suggesting is this. I don't think he explicitly said this, but he's really the idea he's basing this off of. Is this true? That's true. So, I mean, to think about the rationale we used in the last example, we can still use it here. As x gets very, very big, x squared is going to dominate 1, right? So if you look at the limit this way, you know, taking that 1 away, does that make that square root easier to handle? Yeah, that just comes out to x, right? And those of you who have graphed this, maybe you've already seen that that might prove you're suspicious about what this limit is equal to, which is it should be 0. And I am willing to bet that kind of felt a little hand wavy for many of you. Just because you don't have a fraction doesn't mean you can't use this technique here. But like if you can graph it, and that'll definitely work. But if you want a more algebraic way to do this, you can definitely do this right here. X plus 1 minus x times this function. X squared plus 1 plus x. Now, as I'm writing this out, what's going to happen to this denominator as x gets really, really big? As the denominator, so just the denominator, not the whole thing. It's going to go to infinity, right? And what happens when you divide by a really, really large number? It's going to get closer and closer to 0. And now with this conjugate, though, I've really done something helpful by simplifying the numerator. So now I just get 1 over this denominator, which, as you just said, is going to get really, really, really big. So if our other two methods for explaining why that limit 0 weren't totally satisfying, hopefully that one's a little more convincing. Okay, question? When that comes up. We know this is true, right? So, I mean, that's essentially what you're suggesting is that the square root of these two things is equal to the square root of this thing, plus the square root of this other thing, which can't be done. So you can't easily break up the x squared and the one that's got added to it. Any other questions about this one? See what we got left. Okay, just those two. And they're both pretty quick. Unless I keep screwing up. All right, this is like a function we've seen before, but now, I think last time we looked at this weird sine curve, we were looking at what happens when x got closer and closer to 0. Now I want to know what happens when x gets really big. What's going to happen when x gets really, really big? I heard someone say it's going to oscillate, and then somebody said it's going to get, well, so it's always going to oscillate. That's someone else also said it's going to get closer and closer to 0. So remember, we can deal with limits as composites, as long as the inner limit and the outer limit both exist. So can we think about this? What is the limit as x approaches infinity of 1 over x? 0. So then I'm really looking at this. What is the limit as x approaches fill in the blank of sine of x? Undefined. So bottom line, let's just kind of peel the onion. I care about what happens when x gets really, really big, right? But when x gets really, really big, what happens to 1 over x? Smaller and smaller and smaller, approaching what? 0. So then I can reframe this as the limit as x approaches 0 sine of x. Maybe it'd help if I didn't call these both x. And I'll say y is equal to sine of. No, y is not equal to sine. Y is equal to 1 over x. Where is the sine function continuous? Everywhere it's defined, right? Which in this case will be absolutely everywhere. So what is the limit as y approaches 0 sine of y? 0. So again, if it helps you, you can definitely break these things down using composites or products or sums, any of the other ways that I showed you. And real quick, in 2 minutes. Normal reciprocal. What happens so I'm thinking the sine of x. As x goes on infinitely, what happens to sine of x? Is it any bigger? Oop. Yeah, so it oscillates between -1 and 1, right? What is it eventually going to settle on? Absolutely nothing, right? That doesn't exist. So yeah, I mean, this is a periodic function, right? So periodic functions, they have a certain set of behaviors, and they will repeat that indefinitely. And since the sine function just bounces or oscillates between -1 and 1 indefinitely every 2 pi radians, you will not get a limit. There is no number that you'll eventually settle to as x keeps growing. Question? What's that?
Yeah, like something like.
You engineering majors will see a thing that looks like this, or I mean, like you'll have f of t equals e to the -t sine t, and versions of that. That way, that you have a function that amplitudes. That absolutely has a limit as t. Okay. You have no limit. All right, that is 12:05, everyone. I'll stick around if people have questions. Otherwise, I will see you Wednesday. See you. Yeah. Yes. There you go.
Okay.
Go ahead. The quiz?
Yeah.
Can you just put it online?
Yeah.
That's it. Oh, that was, yeah, that's, yeah. If you just graph it out, then that'll tell you.
Yeah.
Mr. Reese, well, you can call me Steven. If you don't feel.
I don't remember.
So talking about what works. I don't really, but you know, it's a weird time right now. I mean, if you need.
No.
Yeah.